Welcome to section 1.5 of our linear algebra notes. Today we're going to talk about solution sets for linear systems. First, we'll look at whether or not the homogeneous system AX equals 0 has a non-trivial solution. Then we'll talk about how to write the solutions in parametric vector form. And finally, we'll talk about the geometry behind the solution set for AX equals B. So first we'll talk about homogeneous linear systems. And homogeneous means that instead of writing AX equals B, we write AX equals 0. And 0 is the zero vector that looks like just a column that consists only of zeros. And so if you think about the equation A times X equals 0, when we do that A times X, what we're really doing is X1 times A1 plus x2 times a2 all the way out to xn times an, and we want that to equal 0. Well, if we actually plug in 0 for our x1 and 0 for our x2 and so on all the way out to 0 for our xn, then of course what we're going to get is a bunch of vectors all multiplied by 0, which is going to make them zeros, and then added up, which makes them 0. So this tells us that the vector x equals 0 is in fact a solution to the homogeneous equation AX equals 0. And it's called the trivial solution. So if we talk about a non-trivial solution, that means a solution other than 0. So AX equals 0 always has the 0 vector as a solution, but we sometimes want to find other values of x. And let's think about what needs to happen if we want a non-trivial solution to exist. Well, if you think about kind of what those vectors might look like, if we have something like, let's just say we have... Let's make this interesting. Let's say we have something that, an augmented matrix that looks like this. I made this up. So this equation, so we have variables x1, x2, and x3, and here are our pivots. So in this situation, x1 and x3 are our basic variables, and x2 is a free variable. Remember, that means that we can change up what the value of x2 is, and then that will impact what happens for the others. And so here we have this top equation says x1 plus 2x2 equals 5. So we can change x2 and get a bunch of different solutions, whereas x3 is going to be fixed. And so we need to somehow have something that we can change up, in this case our x2, in order to have more than one solution. I messed up, because this should be, we are dealing with homogeneous equations. Sorry, so this should be zeros because we're still in our homogeneous land, okay? And the reason I noticed that is because I know that 0 is always a solution, and those numbers I just had before would not give us a solution. Okay, but so here, because we do have this free variable, we might let x2 equal 1, and then we'd see that x1 would be -2, and we'd get a new solution. So we have the solution, let's see, if we said x2 was 1, x1 I believe is -2, and actually we have others. We have one solution for every possible choice of x2. So ultimately what needs to happen is we need a free variable, at least one free variable. And another way to think about this is we need at least one column of A that doesn't have a pivot position. Oops. So we need at least one column of A without a pivot position. Okay. So now our first quiz for today gives you a system, a homogeneous, because it's got these zeros, system of equations. And what I recommend doing is go ahead and write your augmented matrix and row reduce. and see if you have any free variables. If you have, so I'll just write this down for you. So you row reduce, and if you have free variables, there exists a non-trivial solution. If there are no free variables, then you have only the trivial solution. So go ahead and hit pause, do your row reduction, and then answer the quiz. Okay, so sometimes we might see a system that actually only consists of one equation, and that's totally fine. We can still deal with that. We have 4, -5, 2, and if we make the augmented matrix, it looks like this. And in order to write the solutions in, whether it says a span or what we'll see soon is in parametric vector form, either way, it's best to get our matrix to reduced echelon form before writing a solution. So reduced echelon form is most useful for writing solution sets. Echelon form is useful for knowing whether or not a solution exists. So this one's a pretty easy row reduction. We just take our first row and divide it by 4. And so this corresponds to a system of equations, namely it corresponds to the equation x1 minus 5/4 x2 plus, I'll go ahead and reduce that to 1/2 x3 equals 0. It's what we get if we take the equation given and divide it by 4. So now what we want to do is, it says we want to write the solution as the span of a set of vectors. So first of all, let's think about our solutions. So our solutions are going to be vectors that look like x1, x2, x3, right? We have 3 variables, so this is what our solutions are going to look like. And now we know that x1 is our basic variable, and then x2, basic, and then x2 and x3 are free. So we want to write x1 in terms of our free variables. So we want to, in general, write our basic variables in terms of our free variables. This just allows us to use our freedom from our free variables to get different options for our basic variable. So now we can plug that in. So our first variable is basic, x1, so we write down what it's equal to in terms of our free variables. And then our next variable is x2, which is free, so it's just equal to itself. And then our final variable, x3, is another free variable, so it's just, it doesn't depend on anybody else. But now if you look at this, we could actually think of this x2 as being 1 times x2 plus 0 times x3. And similarly, x3 could be 0 times x2 plus 1 times x3. And now we have something that's starting to look like a vector equation. So we can pull out that 5/4 1 0 times x2, and then -1/2 0 1 times x3. And this is a linear combination. And in fact, since we can change x2 and x3, it's the set of all linear combinations of the vectors 5/4 1 0 and -1/2 0 1. So our solutions are exactly the vectors that are in the span of those 2 vectors. Okay. There's one other way that we'll often write our solutions, and that's in parametric vector form. So now we're moving away from homogeneous. And so notice since we have a b that's not necessarily 0, this is called a non-homogeneous equation. And we want to write, first of all, it asks us to write the system of equations in the form ax equals b. So let's go ahead and do that. So we have 1, 2, -1, 2, 1, 1, -3, -3, 0 is our a. Our x is x1, x2, x3. And then our b is 5, 13, -8. So here's ax equals b. And again, if those b values were all zeros, we'd be back in the homogeneous situation. Okay, so we want to find our solutions. So in order to find solutions, we have to start by reducing to reduced echelon form. So we're going to go ahead and convert this into an augmented matrix. And then we will start our row reduction. So let's make that -1 in the bottom row disappear. So we get, let's see, a 0, 3, -3, -8 plus 5 is -3. And then we can skip or not really skip a step, but we can do another step inside this same step. So let's go ahead and change row 2 by subtracting 2 times row 1 from it. So we have 2 minus 2, 1 minus 4, -3 plus 6, and 13 minus 10. And what you should notice is that row 3 is just -1 times row 2. So we can make it disappear. So let's take row 3 plus row 2 in the bottom. I'll go ahead and write down my row 1. And when we do that, our whole bottom row, even the part in that augmented column, is still going to be 0. And then again, I'm going to do 2 steps at once by taking row 2 and dividing by -3. And so I get 1, -1, -1. And now this isn't quite in reduced echelon form because this 2 here, so remember in reduced echelon form, all of our leading terms should be the only non-zero entry in their column. And so this 2 makes that not quite reduced echelon form, but we can deal with that pretty easily. We take row 1 and we subtract out 2 row 2. And so we get -3 plus 2, and then 5 plus 2 gives us 7. Okay, so now we have our equation in reduced echelon form. And now let's go back and write it down as a system. So we have x1 minus x3 equals 7, and x2 minus x3 equals -1. We can ignore that bottom row, and in fact, we could have even done this without it. We could have deleted that whole row and just made a matrix that looks like this. Just the 2 rows, because that is no longer giving us any information, but only because it's all zeros. If there's anything non-zero at all, even in the augmented part, then we couldn't do that. Okay, so we have our 2 basic variables. So x1, x2 are basic, and x3 is free. So our first step is to solve for our basic variables. So we write them in terms of the free variables. So we have x1 equals 7 plus x3, and x2 equals -1 plus x3. So now we're going to do what we did before when we were trying to write our solution as a span. And let's see. So first, x1 is 7 plus x3. x2 is negative 1 plus x3. And then x3 is itself. And what you'll notice is this looks a lot like what we had before, except we have a column that doesn't have any x's on it. And that's okay. We can treat it kind of the same idea. We can treat it kind of the same way by writing a column and then plus a column vector that's multiplied by our free variable. And so this x3 here is also thought of as the parameter. It's the thing that you can change. This isn't quite a span because we're not taking all linear combinations of that 7, negative 1, 0. Notice that doesn't have a variable beside it. It's just fixed. You could think of it as 7, negative 1, 0 plus the span of 1, 1, 1. But it's not, this whole thing together is not a span. So this is our parametric vector form. Okay, so the last thing that I want to talk about with you is how to understand these concepts geometrically. So let's draw the vector 2, 1. And remember, a vector is a magnitude and a direction. And so, in fact, this is our vector v, 2, 1. And what's kind of cool about that is I can copy it and paste some extra copies of it, because ultimately I'm going to want a few of these for what comes up next. And then we also have 2, 2. Now remember, this is a vector and a direction, so I'm going to cheat and put the vector 2, 2 over here first, and then just gonna move it and copy it. Okay. So we have, if we want v plus p, I have v and I add a p and I get v plus p, right? Here is our v and this light blue is our p. And so we get this vector that comes right here. But we can actually just repeat that. 2v plus p means we take our vector twice and then we add in our p. And similarly, 3v plus p, we can do that again. And so what we end up getting is a series of endpoints for these vectors, and then we're asked to draw a line connecting those. And then our final quiz question asks us about what's special about this line. And what you'll notice, and kind of what the point here is, if you think back to what we did up above, it's kind of like we had our vector p here, and then we had a vector v that we could pick any number, any multiple of that vector, add it to p, and see what we get. That's kind of what's going on here. And so our solutions are going to all lie along this one blue line.